Today, we continue the finite element method and its application. So today we'll talk about chapter 8, the structure dynamic analysis. And the structure dynamic analysis is a very important issue, or is very useful tools, because it can be used to analyze many engineer problems. For example, the building under the impact of earthquake, and the bridge also, this is under the impact of the earthquake or the very heavy winds, and the damp, and all those failure of the building, bridge, and the damp, they are not because of the stress. It's because of the dynamic vibration, is the dynamic effect. So the dynamic failure is a very important type of failure. So, and here are some other examples. The stadium, the frame structure, and the electronic power tower, and the bridge. So when we design, as an engineer, when we design those structures, we need to consider not only the stress limit, but also the dynamic. We need to perform a dynamic analysis to make sure those structures are still safe under the dynamic case, or under the dynamic loading condition, or under the vibration, and under the earthquake, and in those loading scenarios. So the structure dynamic analysis, or the structure dynamic, is to analyze the structure dynamic reaction under the dynamic loading. So this is the structure dynamics. For example, what are dynamic loading? For example, is the earthquake loading, the wind load. They are two very typical dynamic loadings. A dynamic loading is the magnitude, the direction, and the loading position are changing with the time. So we know the earthquake. So for the earthquake, the magnitude and the direction and the loading position, they are keep changing with the time. So if the loading is has this kind of property, or have this kind of feature, then we call it the dynamic loading. So this is very different as static loading. But for the static loading, all those variables, they keep the same, and they don't change with the time. So let's do a comparison between the static loading and the dynamic loading. So for the static loading, we have the structure, and for the structure we have the stiffness of the structure, and we have the dimension of the structure. Then we apply the static loading to the structure, and then we output the static response. So what are the static response? They include, but not only those, but more than those, they include the displacement of the structure, the stress and strain distribution in the structure, and also the reaction force. But for the dynamic loading, so we have the structure, and then we need to give the input, like the stiffness and dimension. So those are same as the static loading case. But additionally, we have to input the mass of the structure, the damping of the structure into the structure, in order to perform the dynamic analysis. Okay. And then those are our input, and then our output from the dynamic response are the velocity. So these are the additional variables: velocity, acceleration of the structure, and some dynamic variables: dynamic stress, dynamic strain, dynamic displacement, or those, and also some dynamic coefficients. Okay, so the outputs from the dynamic analysis are different as the static analysis. And also the variable, or the variable we are interested, or the variable we focused on, are different. So for example, in the static analysis, maybe we more focus on the maximum stress or maximum strain to determine whether the structure is failed or not. so it's safe or not. But in the dynamic loading, we more focus on the velocity and the acceleration, focus on those parameters, and we use those dynamic parameters to judge or to give the decision whether the structure is still safe or not. Okay, so these are very different. So for the dynamic analysis, normally we have 4 types of analysis. So we will give a short introduction of each type. The first is the model analysis. The second is the transient dynamic analysis. The third is the harmonic response analysis. And the fourth is the spectrum analysis. So we have a look at the model analysis. So what is the model analysis? The model analysis is to use the overall mass and the stiffness of the structure to find the various period at which it will naturally resonate. Okay, so the job or the aim of this the model analysis is to find the periods at which the structure will naturally resonate. So the model parameter, example, the frequency, the vibration mode are determined by the structure of the property. So from the model analysis, our aim is to find the frequency and the vibration mode of the structure, and also you should be pay attention to the concept. So the frequency and the vibration mode of the structure is only determined by the structure property and not by the external loading. So it's kind of similar to the Young's modulus of the structure. So we know the Young's modulus and the Poisson ratio is the physical property of the material, and those properties are not influenced by the external loading. It's only influenced by the material itself. So similarly here, for the structure, its frequency and the vibration mode are only determined by the structure property. For example, the mass, influenced by mass and by the stiffness. So, for example, here, the building, we have the building. The building's natural frequency should not match the frequency of the expected earthquake. So, therefore, when we design our building, we should not only check the maximum strength, the strength limits. We should check we should work out the natural frequency of the building and make sure this building, the natural frequency of the building is far away from the earthquake frequency. Okay, so otherwise the building will resonate, and when it resonates, it will vibrate a lot, and then you will get damaged. Okay, so therefore when we design the building, we have to work out the natural frequency, and from this sentence we know the natural frequency of the building is determined by the mass of the building, also by the stiffness and by the structure of the building. Okay, so similarly here, the bridge, the frequency of this bridge should be away from the frequency of the people and the car on the bridge. So we know if the car is running or is driving on the bridge, if the people is walking on the bridge, they give a dynamic loading to the bridge. Okay, they give a dynamic loading to the bridge, and then they will cause the bridge to vibrate, and the vibration caused by the car and the people should be away from the frequency of the bridge. Okay, should be away from the frequency of the bridge. Therefore, when we design the bridge, we need to work out the frequency and vibration mode of the bridge, and we should make those frequency far away from the frequency caused by the cars. Okay, so this is very, when you are an engineer, you have to consider all of those. Is very important aspect. So the second is the transient dynamic analysis. The transient dynamic analysis is a technique. So it's is a technique to determine the dynamic response of the structure under the action of any general time-dependent loads. Okay, so the last sentence is the key sentence. Is to determine the dynamic response of the structure under the time-dependent loads. They can be used to determine the time-varying displacement, strain, stress, force in a structure as its response to the loading. And the inertia and damping effect are considered to be important. Otherwise, the static can be used instead. Okay. So this is the transient dynamic analysis. So next is the harmonic response analysis. Harmonic response analysis is a technique to determine the steady state response of a linear structure to loading that vary sinusoidally, okay, harmonically with the time, okay. And the fourth is the spectrum analysis. Spectral analysis is the one in which the results of a model analysis are used with a known spectrum to calculate displacement and stress in the model. It's mainly used to determine the response of structure to random or time-dependent loading, such as earthquake and wind loads. Okay, so we said here it's in which the results of model analysis, we said in the first analysis, the model analysis. So we use the model analysis as the input, okay, and then we calculate displacement stress in the model, okay. So, and the aim, or what is used for, is used to determine the response of structure to random or time-dependent loading, okay. So like if the structure is under the earthquake or wind load, then we can do the spectrum analysis. So among the four analyses, I think the first analysis is very important and is very useful and is very, very common. Okay, the model analysis, you need to work out the frequency and the vibration mode of the structure when you design the structure, when you design the bridge and the buildings, etc. Okay, now some mathematics. So it's only for you to understand, only for you to know. So the dynamic problems, the equation, so don't worry about too much about this, it's only for you to know. Okay, so for the dynamic problem equation, the displacement, strain, and stress are function of the coordinates and the time. So for example, the equilibrium equation, okay, equilibrium equation, for the equilibrium equation for the dynamic problems, so we have two additional terms. So here rho is the density we set for the dynamic analysis, where the response is determined, is influenced by the mass, and V is the damping efficient. Okay, it's a damping efficient, and it's also influenced by the damping. Okay, and here this is the acceleration. This is the velocity. Okay, so with that we have three type of equations in the elasticity for the deformable body. The first is the equilibrium equation, and the second is the strain displacement equation. So for the strain displacement equation is the same as the static case. And then the third is the stress strain equation. This is also the same as the elastic as the static case, but the elastic coefficient matrix is different as the static case, because here we have to introduce we have to consider the mass, okay, and then the boundary condition. Those are all similar to the to the part we have in the previous chapter. So for the boundary condition, we said we have two types of boundary condition: displacement boundary condition and the force boundary condition. Then we also have those initial conditions, and we can use all those boundary conditions to solve the stiffness equation. And then we use to set up the stiffness equation. We use the virtual displacement equation. So we work out the potential and energy. Okay, work out potential energy, and then we can set up the stiffness equation. Then let's have a look the finite element formulations. So this is our previous knowledge. So and now we have a look how we apply those knowledge to solve the dynamic problems. So we said for the FE calculation, we need to write out the node displacement matrix. So this is our node displacement matrix, and but here you see we have the displacement in three directions: U1, V1, W1, and we have the element displacement formulation. So we write it in terms of the shape function and the node displacement matrix. And the shape function is the same as the static problems. And for other variables, you can also formulate in terms of node displacement. Okay, so for other parameter, we mean the string and the stress and the velocity and the acceleration. So those are two additional terms for the dynamic problems. So we have the velocity and we have the acceleration. So the velocity is also where this is the interpolation function. This is interpolation function. So we all use the interpolation concept to solve the problems. Okay. And then the next we use the virtual displacement. We use the virtual displacement. The virtual displacement equation can be rewrite as this form, and then in the end we have the stiffness equation, right? We have the stiffness equation we want. So if you remember, this is the part for the static case, but for the dynamic case we have two additional parts. So one is the term related to the mass, the other is the term related to the damping. Okay, therefore we have the mass matrix and the damping matrix. Okay, the mass matrix and the damping matrix, we all use the shape function of the element. Therefore we always say the shape function of the element is very, very important, and you have to work out for the FE analysis, you have to work out the shape function first. So once you work out the shape function, and you can quickly set up the stiffness equation, and you can quickly solve the problems. Okay, so this is we use the mass and the velocity, and then we can solve the mass matrix and the damping matrix. And this the K matrix, the stiffness matrix, is same as the static case. And then this is the external force. Okay, external force. So once you know all those equations, why we introduce those? So these are not for the commercial software use. These are for you if you are doing your own program. Then you need to know all those formulations, all those equations to do your own coding, to do your own FE program. Okay, so then the next, this is we already mentioned. This is the mass matrix and the damping matrix. Then the next is the global equation. What does the global equation means? Because the previous we are setting up the equation for the element, and for the global equation we have to assembling them together. So here we don't mention too much because we already do many exercises how to assembly the element matrix to the global matrix. So you assembly all the elements mass matrix, and then you get global mass matrix. and this is the damping matrix, and then you get a global damping matrix and the stiffness matrix. Then you get the global stiffness matrix. Okay, and this is the node force, and the displacement matrix. Okay, so then the next is some discussion. So the dynamic case, when there's no mass and no damping, then it is reduced to the static case, and also there are some cases you don't have damping, and then when there's no damping, then it means the damping factor is 0. Then you can further reduce the equation. Okay, and there's another case. There's free damping. Free vibration of the undamped system. Free vibration of the undamped system, which means there's no damping. Okay, there's no damping also because it's free vibration. So there's no external force. The external force is 0. So then the equation is reduced to this format. So this just for you to know, when people they are talking about free vibration of undamped system, what do they mean? They mean this. They are referring to this equation. Okay, this is the free damping equation, and then the solution format. This is use the same idea. So we give to solve this equation. Okay, to solve this equation, we give a trial function. So we guess the solution is in this format, and then you put back into the equation, and then you get those, and then you solve this. So this is still the free vibration of undamped system. Okay, so for this, and then we said we give the trial function, and then in the end we get this equation. For this equation, the condition for the non-zero solution is the determinant of the coefficient this equals to 0, or in other terms this equals to 0, because lambda equals omega square. Okay, here there are some important concept. Okay, important concept. Why this is 0? The determinant of this is 0 because this is not 0. Okay, the displacement is not 0. Therefore, in order to make this to make this term equal to 0, we have to make the determinant of this is 0. Okay, and here, then we have several important concept or the definition. Here, the lambda is called the eigenvalue, and omega is called natural circular frequency. Okay, the natural circular frequency, and it's determined by the property of the structure, the mass, shape, and material. So this is a very important parameter. Okay, very important parameter. And we said in the first analysis of the dynamic problem is the mode analysis. Okay, the mode analysis we have to work out the natural frequency. Okay, for the natural frequency, how do we work out the natural frequency? Actually, it's by solving this equation. Okay, by solving this equation, you can work out the natural frequency, which means you solve the free vibration of a non-damped system. We said the natural frequency is independent of the external force. Therefore, you don't have the external force here. Okay. And here the Q bar is called eigenvector. Okay, we have the eigenvalue, and this is the corresponding eigenvector, or is the mode of the corresponding frequency. The mode of the corresponding frequency, like how the structure is deformed under the eigenvalue. Okay, under the frequency. Okay. So then let's talk more about the mass matrix. The mass matrix. There's two types of mass matrix. First, the consistent mass matrix. For the consistent mass matrix, we use the same shape function as for stiffness matrix to calculate the mass matrix. And by the way, how the mass matrix is calculated, so they have two different types of mass matrix. Okay, so for the consistent, they use the same shape function. So we see here, they use the same shape function as used for the stiffness matrix to calculate the mass matrix. So now we know for this is for the bar element. Okay, this is for the bar elements. So this is a shape function for the two-node bar element. We see here. This is the shape function. Then we can use this to calculate the corresponding mass matrix, and then we get those answers. There's the second type of the mass matrix is the lumped mass matrix. For the lumped mass matrix, and again we use the two-node bar element as the example. So to calculate the lumped mass matrix, we distribute mass equally at the two nodes. So this is different as this. We for the lumped mass matrix, we distribute equally at two nodes. Therefore, you have those. Okay, half in one node, half on the other nodes. Okay, but here for the consistent, we have different. We not only distribute on the node, we also distribute the mass on those locations. Okay, these are different. So we introduce this so to make you pay attention. So sometimes your answer may be different as other people's answer, and in that case you have to check whether it is consistent when you calculate the mass matrix, and so therefore you have to check your procedure. And even when you use the commercial software, it's better you check how they are performing the calculations in order to understand the result, or in order to do the comparison between different analysis between different papers. Okay. So now the FEE formulations. So we already very familiar with this equation. So this is the stiffness equation for the dynamic problems, for the dynamic case. Okay. So the dynamic problem is to solve the displacement q and the velocity q dot and the acceleration q double dot under the force, external force pt, and external force, you always say it's a dynamic force. It must be a dynamic force. You cannot solve the dynamic problem on the static case or static force. Okay. And how do we solve this equation? Now that from this slide we are talking about how do we solve this equation. So we have many different approach. Maybe you have already learned this from the previous lectures. So here we just quickly go through different approach, different method. So the first method is the mode superposition method. For the mode superposition method, we perform the uncoupling on the damped dynamic equation, and then solve the equations separately. Okay, so that kind of we uncouple those equations, and then we solve them separately. Then we put them together. We call it superposition. Okay. And the second approach is the direct integration. So we use the integration method. So we discretize the time and calculate the displacement at each time step. Okay, so this is direct integration is used a lot and used in most FE software. And under this approach, we have the explicit algorithm. And we have the implicit algorithm. Okay, we have two sub approach. Okay. Then first we talk about the explicit algorithm. So for the abacus or ANSYS, for the explicit solver, we used explicit algorithm. But for the implicit or the standard solver, we use the implicit algorithm. Therefore, it's important for you what's the difference between the explicit and the implicit. Okay, and what's the at least you don't need to know all this equation, but at least you need to know what's the difference, or by the sentence you need to know what's the difference. Otherwise, you don't know how to in which case you should use explicit and in which case you should use implicit. Okay. So for the explicit algorithm, we use the value from the previous time step to calculate the results at the next step. So, and at the given time step, calculate the value at each time point step by step. Okay. This will give you the example. So we have the acceleration, and we have the velocity, and those are calculated from the displacement. Okay, these are the velocity is also calculated from the displacement, and then we put all those equations into the stiffness equation, and then we in the end we do the mathematics. In the end we get this equation. And then we said for the dynamic problem, our aim is to calculate the displacement. Okay, is to calculate the displacement, and we are using the integration method as we showed in the previous slide. So we are using the integration method, and for the integration method, we calculate the displacement step by step. Okay, at each time step. Therefore, because we at each time step, therefore you see the time t and time t minus delta t, time t minus plus delta t. Okay, so this is a very typical explicit equation. Okay, this is a very typical explicit equation. Why is it a very typical explicit equation? Because once you know the value of the q at time t and at time t plus at t minus delta t, then you can use the equation to quickly work out the displacement at the next time step. Okay, at the next time step. So so that's why it is explicit, because you can explicitly solve the problem. Okay, it's explicit. It's by its naming. Okay, so in the equation, if we know the displacement at the previous time step, then we can quickly work out the displacement at the next time step. Okay, so that's what we see. We use the value from previous time step to calculate the results at the next time step. That's why when people using this strategy, we call it, they are using the explicit algorithm. Okay. So in comparison, okay, so this is still the explicit algorithm. So we at the initial step we have the acceleration and the velocity. Then at the initial, these are initial time step. So we have time 0, okay, and time 0, and then we have those. Okay, we have those, and where q0, so the velocity at the initial time step. So at time equals to 0, okay, can be obtained through the initial condition. Okay, so when we solve the problem, we have always we give the initial condition. For example, the object its initial velocity is 0, or the object its initial velocity is 2 meters per hour, like this. This is the initial condition, and the initial condition always you know it's a knowing variable. And then the velocity can be calculated from the dynamic equation. Okay, can be calculated from the dynamic equation, and therefore this the displacement at this time point can be worked out. Okay, so some discussion about the explicit algorithm. For the explicit algorithm, there's no need to calculate the inverse of the stiffness K. Okay, there's no need to determine the inverse, because we see if we go back to the equation, you see here we don't need to inverse, and we just need to know all those parameters, and you can quickly work out this. There's no need to determine the inverse. Okay, so this is the advantage. This is a very, very good advantage, because for the program, for the coding, the inverse of the matrix, it will take very, very long time. Okay, it's very hard to do, or it takes much computational power to do this, to do the inverse. Okay, and the other thing is in the FE, when FE analysis, always you have many elements, and then your stiffness matrix is very, very large. And under this case, the inverse is horrible. It will be very, very hard to do. Okay, and in the dynamic problem, the stiffness matrix is changing, and therefore it can save a lot of time. So it's saying for the dynamic case is even better to not calculate the inverse of the stiffness. And the dynamic second sentence is a dynamic analysis is applicable for the wave propagation problems. Okay, because it is using the explicit algorithm and using the explicit, so you can use the previous value to calculate the next value. So in comparison, we have the implicit algorithm, or sometimes we call it the Newmark method. So let's have a look. What is implicit algorithm and what's the meaning? Okay. So again, we have this. This is our velocity. Okay. This is the velocity at time plus delta t at this time point, and then we have those the acceleration, and then this the displacement at time plus delta t. Okay, and then we have and this is a function. The velocity is a function of the velocity at the previous time step, and also a function of the acceleration. Okay, so in these equations, alpha and beta depends on the integration accuracy and stability. And from the second equation we have, so we this equation we will rearrange. We just rearrange the equation. Then we can, if we rearrange, then we have the acceleration at time plus delta t, and we express this variable in terms of the displacement, the velocity, and the acceleration, and then we write this our dynamic equation at t plus delta t, and then by doing all those mathematics, okay, we put all those into our dynamic equation. Then we have this form. Okay, we can say this is much more complex than the explicit algorithm. And also we have look. Okay, you see, this is the parameter we want to solve. Is the displacement at t plus delta t, and we can say it's a function of this. It's a function of previous displacement. It's a function of the previous velocity, previous acceleration, and etc. Okay, and then we do the calculation again, and then in the end we have this equation. And where the matrix K equals to this. Okay, the K equals to this. Okay, so in order to calculate those, this variable, we need to calculate the inverse of this, because we need to put like a qt plus delta t will equal to this the inverse of this, and then times of those. Okay, so we need to calculate the inverse of this matrix, which contains the stiffness matrix. Okay, stiffness matrix, and because the stiffness matrix is changing, therefore a lot of calculation need to be performed, and the unknown displacement and dynamic equation are all at time t. Therefore, it is implicit algorithm. Okay, the unknown this and the dynamic equation, like those, they are all at the time t plus delta t. Therefore this is implicit algorithm. Okay, so implicit or the Newmark method is not recommended in the dynamic analysis. In the dynamic analysis, usually the commercial software they use the explicit algorithm, because save the time computational power, and it's also easy for the program. Okay, so just remember this. And the implicit is more used for the static case, for the static analysis. Okay. So in the end, let's have a look at an example, the free vibration case, free vibration of a ladder bar. Okay, we said from the free vibration analysis, we want to calculate the natural frequency and the vibration mode of the structure. Okay, because it's a free vibration, so therefore there's no external force. So we have some physical property of the deformable body. We have the elastic modulus, we have the mass density, and we have the dimension of the structure, the cross-section area, and then we want to work out the frequency and the mode of the bar. Okay, so to work out this, we need to solve the free vibration equation. Okay, as we showed in the slides. To solve this free vibration equation, we need to first work out all the stiffness. Okay, the stiffness matrix and the mass matrix. Okay, the mass matrix and stiffness. And it's free vibration, therefore there's no damping, so we don't need to work out the damping matrix. And those are solved by this we already mentioned. This we use shape function and then we put it into the equation, then we can solve this. And we can see this is we said we have two strategies to solve the mass matrix, and here we are using the consistent mass matrix. We use this approach to solve the mass matrix. Okay. So then next, and then this is our the free vibration equation. This is the free vibration equation, and we already solved the stiffness matrix, the mass matrix. Okay. Then we can put it into this equation to solve it. And in this equation, omega is the frequency. Okay. And this is the displacement vector. And because we have two elements, so we need to assemble them together. We put the element stiffness and element matrix into the global matrix. Okay, and we know this is not zero. Okay, therefore to make this equation equal to zero, we have to make the determinant of the coefficient equal to zero. Okay, and then we just do the mathematics here to solve this. We have this equation, and then we put the value of k and m into the equation. Then we have this equation. Okay, so this is for you to do the exercise. Okay, whether you can solve this, and we set this. Then we have this value. So from this we can easily solve lambda. So lambda 1 is 0, lambda 2 is 1 over 2, and lambda 3 is 2. Okay. And we said this is the eigenvalue, and then omega. Then we can, this is the frequency. Okay, then we can because then we use this equation to solve the omega. Okay, then omega 1, omega 2, omega 3, and then we back to the equation. We put it all those values back to the equation. Then we can solve Q1, Q2, Q3, and we said Q1, Q2, Q3. This is the mode, okay, the vibration mode, okay, and this is the frequency, this is the vibration mode, and this is what we want, and this is what we need, and those are important property, or we should say the physical property of the structure. And when you design a structure, you need to know the physical property of those parameters, okay, not just the Young's moduli and Poisson ratio, but also the frequency and the vibration mode of the structure. Okay, now let's plot the mode, the vibration mode. So in the first case, okay, so the whole structure move to this position. Okay, this is the first mode. The second mode is they move like this. This is 1, the other one is -1. This is the second mode. The third mode is like this. It's like a triangle. Okay, like this. These are the three natural modes of the structure. Okay, so that's the end of this chapter, the dynamic problem or dynamic analysis. So we just give you a quick overview of all those theories, but in a real situation, you have to do more practice, to do more examples in the software analysis or APGAS, and to understand those dynamic analysis. And we said dynamic analysis is a very important type of analysis when you are doing the design of the structure, or when you check the safety of the structure. And we hope in the future you will use those knowledge to help your career. Okay, thank you very much. Okay, I'll see you next time.